So to prevent creep failure, increase melting temperature, lower the ambient temperature, or increase the grain size. Or maybe another solution is lower the stress you apply to that material. Okay. So by doing those, you can prevent creep failure. So now let's look at what's the result creep test we get. Once again, for fatigue test, the result is called Ascent diagram. So for creep, we also have a diagram. Creep test. The diagram is creep strain versus time diagram. So it's a strain, which is a change of deformation, versus time. So the diagram looks like this. On the vertical direction, we have strain, the creep strain. On the horizontal direction, we have time. One question here, what's the unit for strain? What? No units? Yeah, that's unitless. There's no units for strain. Okay, so the typical creep strain time diagram looks like this. It's a nonlinear curve. And if we look closer here, at the beginning, once that stress is applied to the material, you're going to have this instantaneous deformation. If that makes sense, right? When you apply a stress to a material, there will be either plastic deformation or elastic deformation. So when time you just apply the force to the material, you're going to see a deformation. That deformation gradually increases. So under the same constant, so here this diagram is tested under constant stress. So even we're keeping the same constant stress, sometimes that stress is way below yielding stress. But as you can see on the diagram, the strain increases, which means the deformation is getting larger and larger. So on this diagram, we have 3 different regions. Let's call this region 1. Region 2. Region 3. So at region 1, the name of that region is called primary region. Region 2 has a name too, it's called secondary. And region 3, it's called, I couldn't pronounce, tertiary, T-E-R-T-I-A-R-Y. Tertiary, is that how you pronounce that? Okay. Yeah. So on that curve, something's important. New terms, it's called strain rate. So it's a strain's epsilon. You add a dot. That means it's a derivative with respect to time. So that equals the change of strain divided by the time step, time interval. This is called strain rate. That tells you how fast that deformation changes. As we can see from those three regions, at region 1, how that curve is changing. The curve starts very steep and it goes less steep, right? It's so the strain rate, the slope on that curve tells you what is the strain rate. So that's a slope. Here's a quick quiz here. From the stress strain diagram, what is that slope called in that linear region? Stress strain diagram, that's tensile stress. That linear region, slope is called Young's modulus, or modulus of elasticity. Okay, here the slope is called strain rate. Okay, at the first region, that strain rate decreases. Over time. And at the second region, the strain rate is a constant because that's a linear region. In the third region, that strain rate increases. So what is happening at the end of that curve? So at the beginning, we have some deformation, and that deformation gradually increasing, become larger and larger, and in the region 2, it keeps constant, but still increasing at the same rate. At region 3, that strain rate accelerates. What is happening at the end of that curve? Fracture, yes. And here we also call it rupture or fracture, the way. So in the region 3, that's when the material breaks. Failure occurs. That's a typical creep strain versus time plot. Okay, now my next question for you is, if we increase the temperature, how would that change this plot? Once you look at that plot, if now let's increase the temperature to 500 more degrees, how would that affect the diagram? Let's go back here. Temperature would affect creep. Higher the temperature, more creep you're going to see. So if we're going to draw the strain time diagram, if we increase temperature, that's what you're going to see here. So now I have 3 different temperatures. Let's call this T1, T2, T3. Stress time. So here, T2, it's a higher temperature, larger than T1. T3 is larger than T2. So higher temperature you have, this curve is going to get shorter and shorter. That means it's going to fracture in less time. Right? It's going to break in less time. So same thing happens if you increase the stress. So this is under same stress. So here, let's draw another diagram. What if we increase the stress, increase the load? Well, each curve is tested under the same load, but that load is gradually increasing. Now let's keep same temperature. You're going to see the similar trend. Now the variable here is stress. Stress 1, stress 2, stress 3. Oops, sorry. Made a mistake here. The vertical direction, it's strain instead of stress. Here. That tells you whenever you increase stress or temperature, it's bad. And it increases the risk of creep failure. Okay, so that's all you need to know about creep. So far, 3 different types of failures: fracture, fatigue, and creep. Okay, any questions about creep failure? Okay, now let's do a summary. Imagine you're a senior, you're all seniors, you're doing senior design. And you need to have a piece of metal used in your design project. And how to choose the material? The geometry of the material will affect how much load it can take. The type of material going to affect the range of stress you can apply to that material, right? But what's the thought process? What's the first thing you should do? Oops, what is going on? Okay, so once you have that stress, you can find stress strain diagram from different materials, right? SS curve. And you can compare that stress to all the yielding stress to make sure your material, the stress you applied, it's less than yielding stress. Of course, you have to consider safety safety factor, depends on what type of design you have. But the goal is we want to make sure our stress is way below the yielding stress. So that's under ideal case. That's what we learned during the first 3 weeks in this semester, right? Everything we do is make sure the stress won't beyond or larger than yielding stress. Once it's larger than yielding stress, permanent deformation will occur. Then you have to, everything's broken, you have to replace it. But from this chapter, and we learned, hey, even the stress, the load, sigma load is less than yielding stress, bad thing can still happen, right? There are a couple of things that can happen. First one is fracture. Could happen when you have cracks or flaws, right? Remember, when you have cracks and flaws, those cracks and flaws are called stress raisers, so that will raise or increase the stress along the crack and flaws. So end up you have much more larger stress along the cracks that could cause crack propagation, lead to fracture. Even the load that you apply to the whole material is less than yielding stress. So that's first thing you need to check. Did I consider flaws in the material? Next thing you need to check is, do we have fatigue failure? Is this part subjected to fatigue failure? What's the condition for fatigue failure? That's when you have dynamic load, right? You have the stress, even the stress is very small, but you have circular stress is applied to that part. You ask yourself, is this product ever be used under situations like this? If the answer is yes, you have to consider fatigue failure and check what is the accident diagram to make sure the part you designed can last long enough. Okay. Next thing you need to check, is there any potential for creep? So that's the last thing. It's for most of designs, maybe not a problem because we're not using very high temperature. But you're dealing with rocket or jet engines, and creep failure can be very important. Or maybe you're working with a power generation plant. So everything, they're burning fuel, everything is under high temperature, and creep failure has become more important. So you need to check what is the strain, creep strain rate, strain versus time diagram to make sure design is valid. So as an engineer, it is your responsibility to check all those things, right? That's the difference between a engineer and a farmer. A lot of farmers are very good at design stuff, but they probably never consider those restraints and situations. Okay. All right, that's all about chapter 8. Any questions? We're done with chapter 8. We only have one last part left for this semester, which is phase diagram. It's, for me, from my perspective, it's a little bit boring and dry, but that's something we're going to learn in the next 2 weeks. But this is chapter 1-8. Any questions? Okay, we have about 15 minutes left. Now, I want to use those time for your project. Remember, you have a homework due on Monday. You have to plan out your video presentation. I'm not talking make a video by Monday. I'm talking about you have to write everything, words, so that when you actually making the video, you have a transcript you can maybe just referring to, right? I'm not suggesting you read from that transcript, but you know, at least you have a good idea what you're going to talk about. To be honest, I don't have a rubric for your presentation. I think you're all unique. You have your own ways to present something. So instead, I want you to tell me what's the rubric I should use to grade your presentation. Right? I don't want to limit everybody. So we end up with 30 videos like exactly the same way of presentation. I want to see a variety of different ways to present things. So besides your transcript, you need to tell me what are the rubrics. I think for your video presentation, it was 10 points. So you can tell me, you're going to tell me, give me a rubric to say, okay, this is what should I do to get 10. This is what should I do, what I would do to get 8. So if you don't do such things, you don't get 6 or 7 or 5 points. So you're going to tell me a rubric. So once you submit your project, your videos, I'm going to grade you based on the rubric you give to me. Does that make sense? Okay. All right. So next thing, 10 minutes. I want you to maybe form small groups to just discuss and talk to each other and to kind of get an idea how share with your thought with people around you, and what's your plan to present the material you selected. So I know first we have a couple students select stills, so all the still people can maybe form a small group and to talk. We have a lot of students have carbon fibers. You guys can form a small groups to talk about carbon fibers. Yeah, so next 10 minutes, just feel free to form small groups and to talk. I'm gonna work around, talk with you guys. All right, go ahead. Right, for student on Zoom, I'm gonna put you guys in breakout rooms so you can discuss with each other. So wait a second. Okay. 2 rooms.